So this is an introduction to free probabilities. The very first lecture is going to be about classical probability, the normal laws, and the Poisson laws. Very classical stuff, but explained somehow in an abstract way. So the idea with free probability is that this is not very complicated. It's just an analog of classical probability, and the theory somehow goes the same as in a classical case, provided that you look at the classical theory a bit in an abstract way. So we're going to do the work today and also in the next lecture, like presenting probability theory in a somewhat functional analytic way. And then we'll develop free probability in the other lectures. And it's actually going to be easy if we manage to get the probability that we know, the usual theory, in a kind of more abstract way. So let's find this presentation first. Here we go. So normal and Poisson law, as I was telling you, this is actually an introduction to probability in general, but well, what's most interesting in probabilities are the normal and Poisson laws. That's why I chose this title. So what's the plan first? So first to look at the normal law, that's of course the most important one. And then we'll look first at basic things, the central limit theorem, then a bit of more advanced theory like moments, things like that, a bit of relation with groups and spheres, and then the Poisson law, the same thing. So basic things, and then more advanced aspects, moments, partitions, things like that. So let's get started. Well, the starting of everything is the Gauss integral, of course. So that's your formula. Integral of e exponential of minus x squared is square root of pi. And this is very tricky. So the simplest proof is by doing this trick, you compute the square actually of the integral in the complex plane using polar coordinates. So let's see how this works. So the square of this is a double integral of exponential of minus x squared minus y squared. Now it's polar coordinates, so x is r cos t, y is r sin t. So the exponential is just exponential of minus r squared, but I have to put a Jacobian here. R is the Jacobian, and then I integrate. So 0. So r goes to 0 to infinity, and t the angle the whole way from 0 to 2 pi. Now, if you look at this integral here in the middle, so there's no t here, it's enough to integrate this and then to multiply by 2 pi. And here, actually, I have a derivative of something, you see? So if I evaluate this at infinity is 0, and that 0 is minus 1/2. So you get finally the length of the interval here, 2 pi over 1/2 pi. So the Gauss integral is square root of pi. Very tricky. Now with this, we can talk about Gaussian laws, right? So the problem, every time we define a measure, we have to take care of the mass must be 1. So these laws, you all know about them, but the fact that the mass is 1 is exactly the Gauss integral. I mean, the Gauss integral computes the coefficients here with 2 pi that you have to put in front of the measure for the thing to be of mass 1. So that's your normal law, and then the normal law of parameter t, we'll use that too. I will use notations here, G1 and GT. That's what I was telling you in the beginning. So there's slightly different notations than in a classical case because we want to do free probability afterwards. So we need a lot of letters for this and symbols for these measures. And the idea is that you have somehow discrete and continuous and real and complex and classical and free. And best is to use, for instance, G1 and GT will be the normal laws. The complex versions will be with capital G's, and then the free versions will be gamma. Gamma T with gamma normal and capital, which agrees actually. That's the semicircle law, the circular law. So and same for Poisson and the others. So that's why I use these letters, because when you do free probability, it's better to do it in this way. Also, we'll consider only centered Gaussian laws. So you see G1, well, that's what's called X01 usually. That's N0T. We won't need variance. Of course, all that we do, you just translate. You can translate all the results. So as I was telling you, this is the definition with this notation, which has, you'll see later why we're using this notation. As I was telling you, the mass is 1. That's from the Gauss formula. So let's go back. If we do this change of variables, you see minus x squared. I want to get minus x squared over 2t. So I do this change of variables. So I get square root of 2 pi t. That's what I have to put here. Now, as a first thing, let's try to compute the variance. And that's a very elementary thing. So the claim is that this is t for GT. How to compute it? So these are centered. So the variance is just the second moment, right? So let's compute the second moment. So I put my my log here, and I put an x squared here. I insert an x squared here, and then well, this thing you can write it this way, and now you can do a partial integration. So you see, you integrate this, you take the derivative of this. And the term at minus plus infinity, this is 0, so it doesn't matter. So you get this formula here. And now what happens is that you have this t here, but for the rest, it's just the integral of gt. I mean, that's 1. So just this t is left. Okay, I'm using the Gauss integral if you want once again. So the second moment in t, so that's your variance. Once again, probability, this is denoted sigma square. Here I'll use t once again. There are reasons for doing that because this measure form a one parameter convolution semigroup with respect to t. That's important for what we're doing. So we use t instead of sigma square. Now, what else can we do? Let's compute out the Fourier transform in order to prove the CLT. So first of all, I'll use once again, there are many notations. I'll use this very simple formula for the Fourier transform without any kind of normalizations. So expectation of IXF. And the thing is that this, or rather the logarithm linearizes the convolution, y just by Fubini. So it's just straightforward, it's just Fubini. So that's going to be the Fourier transform. Okay, it's just the simplest formula with any minus or pi or something. It's just the most basic thing you can, basic notation, and that's the good one for what we want to do. Now with the Fourier transform, let's compute the Fourier transform of the normal law first, and then we'll prove the central limit. So the claim is that we get exponential of minus tx squared over 2. So why is this true? So let's go back. Yeah, this is the expectation of e to the IXF. So I have to take, that's my formula of GT, and I have to add this term here, exponential of IXY. Now, if you want to compute this, it's obviously it's a square, right? So we make a square like this, and this is the term left. And now what happens is that, well, I made a square so I can denote this guy by z. So the square is just this thing. And then when I write z is y over square root of 2t, dy changes. So there is a square root of 2t factor, which comes in here. So the normalization constant is just 1 over square root of pi. So I get this. And now, so the integral is with respect to z. So this exponential of minus tx squared over 2 goes here. And the rest, it's once again, is the Gauss integral is 1. So you get this, okay. Every time we're using the Gauss integral. Now, as an interesting consequence, you see these measures from a one parameter semigroup with respect to convolution. I mean, if you go convolve GSGT, get GS plus T, that's a very hard computation actually with the Fourier transform. You have fun with that. It's once again making a square, but it's long. With Fourier, so remember from the last slides, that's the formula. So now you see the log of the Fourier transform, if you want, is linear in t. So you get this right away when the Fourier transforms coincide. Okay, now we're ready to prove our first US theorem. So why is this important? Well, the normal law appears everywhere in nature, no matter what you measure. Like if you take a point here, you measure the temperature, it's going to be a bit Gaussian around the average. So many other things. Also on grading, some like exams, it's always a Gaussian bell like this. So what's the reason behind all this? Why do we get always the normal law? Well, it's the central limit theorem. So the idea is that if you compose things which are independent of the same nature, you get a normal law. So that's the mathematical statement. If you take random variables which are a centered, same variance t, then the averages, which are not exactly the averages, are rescaled by our square root of n, follow this law gt when n goes to infinity. So as this true, so I'll prove it with Fourier. We'll prove that the Fourier of this equals to Fourier of this. So I already know the Fourier of gt, we'll compute it. Now in order to compute this, so what was the formula for Fourier? It's expectation of exponential IXF. In terms of moments, you get this series, right? It's a series in terms of moments. You just take the series of exponentials and you integrate. So you'll get the moments of f which will contribute, and that's the formula. It's just an exponential, okay? And now, by using this formula, now let's compute the Fourier transform of this. So since these guys are independent, since Fourier, log Fourier linearizes the convolution, it's enough to take the Fourier transform of one of these guys, then divide by this square root of n and raise to the power n. Now, here we're interested in the n goes to infinity behavior of this. So it's just enough to compute the term of order 0 and 1. The other ones won't matter. And well, use this moment formula here, and that's what you get here. And now this guy here, you see it's 1 minus something over n to the power n. So in the limit, it's exactly the exponential of that thing here. So you get this. But this was exactly, let's see, exponential of minus t x squared over 2. That's what we had here. So these guys have the same Fourier transform, so they're the same. So that's the proof of the CLT. Okay, very good. Now let's go into more advanced aspects. So first interesting thing is that you see any probability measure you can play with it, compute all these kind of transforms. We already computed the Fourier transform, but there are many other things. And the particular interest are the moments. So for the normal law, these are given by this formula. So it's basically double factorials, well, rescaled by power of t, which is the parameter. Double factorials, once again, that's the convention that we use here, and it's the good one for what we want to do. By definition, a double factorial is 0 and k is odd, and otherwise it's the product 1, 2, 3, 1, 3, 5, 7, and so on up to k minus 1. Okay, so why is this true? Well, we already computed the second moment. How is it a partial integration? So do the same thing here. So that's the moment. I mean, I just take the formula of gt and I add this term here next to the k. Now, if I want to do my partial integration, I write this in this form here. It's exactly as for the variance for the second moment. So the idea is that this is the derivative of itself times something which multiplies to the xk, and that's what you get. Now you apply the partial integration, so integrate this, derivate this, and well, at infinity everything is 0 because you have the exponential. So you get this guy here, and now let's see what we have. So this is an integral with respect to x. This is constant, tk minus 1, so it goes in front of the integral. And what's left here is exactly the moment of order k minus 2, right? So we get the moment of order k, tk minus 1, moment of order k minus 2. So we have a recurrence. I mean, what I'll get here, mk, up to these powers of t, it's going to be k minus 1, k minus 3, and so on. So it's a double factorial. Of course, if k is odd, we end up at the end of the first moment, which is 0. So it's 0. So that's your formula. And of course, the powers of t are exactly these ones. I mean, you see, when you make the descent by 2, it multiplies by t. So it's somehow the square root of t, which matters there. So these are the moments. Now, this is a very nice formula, but can we do better? And yes, we can. So this is even nicer. The moments of the normal law are this thing here, once again, up to the t factor. It's the number of pairings of 1k. So you see, it's exactly what I was saying before, that instead of double factorials, I put this, which is a bit better somehow. So why is this true? Well, I'm just using here the fact that if you take 1k and you're trying to count all the possible pairings, that's k double factorial. Why? Because 1k is odd, of course, you cannot pair them. And so it's 0. And when k is even, it's recurrence. I mean, you take your points 1 to k, you pair 1 with something, there are k minus 1 choices here, and then you're left with k minus 2 points that you have to pair. So that's your recurrence formula. So it's exactly as before. You get k minus 1, k minus 3, and so on. So it's double factorial. So you see this, let's go back to a previous slide. I think it's a bit better than k double factorial. And now we can do even better. I mean, this t here, get it somehow inside. This t has a combinatorial meaning too. My claim is that we have this formula, the moments of gt is just the sum over all pairings of t to the number of blocks of the pairing. Why? Because the number of blocks is k over 2, right? I mean, pairings, I regard pairings as partitions. So the blocks of the partitions are exactly the same here. They're k over 2. So this looks, well, it's just having fun with the formula before, okay? But this is even better because we'll see later that it's related to cumulants and things like that. So that's the good moment formula. If you want to do advanced mathematics, that's what you need, this kind of thing. We'll get back to it later. Now, let's do some kind of first application. So it's going to be very mathematical, but once again, we're not doing probability here in the classical probabilistic way. Our goal is to have a look at probability, which is helpful for doing free probability afterwards. So one interesting problem is that of understanding the hyperspherical laws, meaning the laws of the coordinates of the usual sphere in Rn. The usual sphere in Rn is denoted as a -1 because it has dimension -1. So, well, let's start slowly. So at n is 2, the sphere in the plane is just a circle. So the coordinates are cos t sin t, right? So now if you want to understand you take a product of these coordinates. So it's a power of cos, power of sin. And you want to integrate, and the nice formula is actually just over a quarter of a circle. It's better written in this way. So that's what we want to compute. Well, I guess you're all used to this kind of things. When teaching calculus, you always have fun with these things for p cubing 1, 2, 3, maybe 4. So that's the formula in general. It's the same proof. I mean, partial integration and then recurrence, double recurrence. Okay, so that's the thing that you do 100 times when you teach calculus. Every time you teach calculus, and that's the general formula. So you have a power of pi over 2, depending on the parity of p and q, and then all these double factorials. And Well, it's a bit complicated. That's why we don't teach it in calculus and work out instead of the particular cases, which actually it's actually a very good thing, very good to the partial integration. And yeah, so that's it. I mean, it's the usual thing that you know, but it's not in general. You get a double recurrence, and that's what you get, power of pi and then these factorials. So at any two, it's solved. I mean, we know everything. I mean, these are the two coordinates on the circle. We take an arbitrary product of coordinates, that's your formula. So everything is solved. Now in general, let's do the same thing in general. And here for the n sphere. And here the result is best written in this way here. So just take a product of coordinates xi1, xik. And I won't collapse, I won't use exponents. It's better written in this way. So I just take an arbitrary product like this. The indices can, of course, be, they're not supposed to be disjoint or something, they're arbitrary. So this really computes all the integrals over the sphere. So it's this big product of double factorials. So it's like a multinomial coefficient. I mean, you see the sum here of all the guys here is equal to the sum here. So it's a multinomial coefficients, but in a double factorial sense, where LA are the exponents, if you want. This thing, if you collapse its powers of each XA to the LA, it's a product of things like this. So these are the exponents. So how to prove this? Or how to compute this? I mean, if you don't know the answer, of course, so how to compute this kind of guy? Well, you use spherical coordinates, right? So you have your monomial here in the coordinates, and then T1, these are the angles, this is the Jacobian, and then it's actually better to integrate only over a quarter, there or 1/8 or a power of 2, the first quadrant if you want in n dimensions. So that's why everything ranges from 0 to pi over 2. And we have this factor here to the n. And then you have to divide, of course, by v, the volume of the sphere. Now the volume of the sphere, well, 2 to the n over the volume, is something with a gamma function. And actually it's as simple as this. It's just a double factorial with this pi factor here. That's why, I mean, the double factorial convention is very useful, for instance, for the volumes of spheres and many other things. So you have a double factorial here, which is the one here, and the rest, well, by Fubini, I mean, now you have these angles. So it's you have to solve n problems in 2 dimensions if you want. So use this formula here, okay, for cosine sin, and you get your double factorials. That's what you get. Okay, so this is reduced the polar coordinates, reduced everything to integrating powers of products of cosinus and sinus of the various angles. So use that formula and you get this. Now let's see what happens when n goes to infinity now. So this is, well, first of all, let's take just one variable. That's the hyperspherical variable. So this formula before reduces to this. And the point now is that these variables rescaled by square root of n become normal when it goes to infinity. So that's the relation of the normal law. So the coordinates over the sphere become normal. And why is this true? Well, let's take a look at this when n goes to infinity. So k double factorial is fixed, and the rest, well, you have to imagine it's like if you take a usual factorial divided by another one, when n goes to infinity, you have to, it's n power the difference of the sizes of the factorials. So the difference of the sizes here is k, but since you have double factorials, which are a bit sparse if you want, it's just 1/2 of these things which contribute. So it's n to the power k over 2k double factorial. And double factorial does the moment of G1, the normal law. So you see we get this is this. So if I get rid to this factor here by normalizing my variable like this, I get precisely the moment of G1. So this becomes normal. Okay, very nice. We have a first application of the normal law. So this coordinates become normal, but then it goes to infinity. Very nice. And Actually, well, this is a simple consequence of this. It's much more powerful because it gives you the joint moments of all the coordinates. And if you play with that a bit, with the big formula, you get to the conclusion also that they're independent when it goes to infinity, these guys. But yeah, that's we'll be back to this later in other lectures, so no need to prove that. That's quite nice for them that they are normal, but it's good to know that they're independent too. That follows from the previous formula. Now, one more thing regarding the normal law. So you take the group of rotations in Rn. This is ON, it's called. And the point now is that this has n square coordinates, right? These are the n square coordinates of the matrices. And these coordinates each follows a hyperspherical law. That's something classical. Even more is true that if you take any row or column of coordinates on ON, that's exactly a sphere. And the uniform measure on ON corresponds in this way to the uniform measure on the sphere. So it's exactly the same thing. So now you just take the formula before and you get the moments of the coordinates over ON. That's a consequence from what we did in the previous slide. So that's very nice. Now, so not only you have the result for spheres, but also for orthogonal groups. Well, it's the same thing, but this is a purely group theoretical result, so very interesting. And once again, you can prove that the rescale variables become independent when n goes to infinity. This is more complicated because if you take coordinates on the same row or same column, as I was telling you, that's a sphere, so you get it from the previous result. That we actually didn't prove, but the proof is not complicated. But the point now is that if you take coordinates which are, for instance, on the diagonal or things like that, you cannot use real spheres. You need group theory techniques here. So this is something that we cannot prove for the moment, but we'll prove it, of course, next time. Okay, so that's pretty much it regarding the normal law. So very interesting CRT, of course, that's the main result. Proof with Fourier. And what else do we know? Well, moments are related to pairings, very interesting. And also these things with spheres, rotations, all that. There's a bit of group theory and geometry and all this. So I'll get back to this later. Now, let's go into the Poisson law. Calculus. So, well, everything, well, these things were maybe a bit complicated. So let's have now a few slides, but let's have some fun and relax. So calculus, these are three things that you need to know about E and pi in order to deal with the Poisson law. So what's pi? You take the unit circle and you have two possible things that you can do. You take the length of it and you divide by 2, that's your pi, or you just take the area of the unit circle, that's your pi again. So hope everyone here present knows why these two things are equal. And if you don't, exercise, well, you can actually do triangles when you discretize the problem, take a polygon. Then you compute the area of the polygon, that's half of the this times this for any triangle. And when you sum, so it's finally half of the radius times this thing here, which goes to the length of the circle, so they're equal. So that's the reason why pi defined like this is exactly as pi defined like this. Now, for E, it's the same thing. I mean, you have three things. No one really knows what's the definition, what's theorem. It depends on where you learn, which country, which period, whatever. So all three things are good, and you need to know them all. So that's the first one, limit of this, or the sum of inverses of factorials. Or it's just f of 1, where f is a magic function, whose derivative is itself, and at 0 is 1. Because the solution is here, of course, you can always dilate them. So that's just a normalization. So once again, why are these the same things? Well, this is more complicated. So 3 and 2, actually, it's very easy to pass from one to the other, because if you want to solve this as a Taylor series, you get it by recurrence. You need these factorials, right? So 2 equivalent to 3 is quite simple. And 1, well, you have to do some computations there. 1 is equivalent to 2, actually. It's a bit tricky, but you have to do it. So E defined like this, like this, like this is the same thing. It's a bit as for pi, but more complicated. And finally, last theorem is that you have this. Well, it's more or less, I mean, exponential of it is cos t plus I sin t, and just terribly complicated. So once again, well, I guess most of you are students, but there are some teachers among you. When you teach your first calculus lecture, you'll see that it's quite hard to understand all this. What's the order of these things? What's definition? What's theorem among all this? And how to do your best in order to prove this? It's quite tricky. Of course, you have books, but not all books are good. So, yeah, well, it depends. But this is really very, very deep things. I mean, it's probably much deeper than the whole mathematics, which was developed in the last 100 years or so. I mean, this was developed in a few hundred years. So it's very, very deep. Okay, so let's assume that this is known. Now, let's do some magic. So the number E, let's go back to it. So pi is something very concrete, but E, after all, say, like, what the hell? I mean, why are we interested in this thing? And how can we make it appear in a very natural way? Well, here's your way. So take a permutation of n points, and the arrangement means that any of the points is moved by the permutation. There's no fixed point. The probability for sigma to be at the arrangement is 1 over E when n is big. So that's how you get your E out of nothing. So as the proof of this is the so-called inclusion-exclusion principle. So you take that's your symmetry group. You take F1 permutations fixing 1, F2 the permutations fixing 2, and so on up to Fn. Now I want to compute those with the range everything. So it's what's left here outside the union. And how to compute the complement of the union. It's the so-called inclusion-exclusion principle. You take everything, then remove all these guys. But the problem when we remove is that the intersections, you remove them twice, right? So you have to add back the intersections. But not the intersection of 3 sets. If you think a bit, you put them once here, you remove them how many? 3 times here, and you add it 3 times here. So you have to remove them. So it's something like this, an alternating sum. Now the cardinality of these guys, of course, if I is fixed, the rest must be permuted, so it's n minus 1 factorial, right? And same here, it's n minus 2 factorial and so on. So this kind of sums, you have some factorials and then some binomials here in order to make your choices. So you get the sum of binomial, no factorials, right? You get exactly this with signs, and that's the series of 1 over E. And that's your probability. So you see that's how it appears in nature. Now, well, maybe more about pi. Let's have some full fun now. So how to get pi via a kind of experiments. So before the experiment was just take n guys and tell them to move. They are sitting on chairs, tell them to move, and many times. And if the number of guys is big, you get your 1 over E. Actually, the convergence is very fast. I mean, that's the convergence. You see, so if you have 10 guys, that's enough for having a lot of good decimals for E. Now, how to do it with pi? That's the so-called Poisson needle. So take a needle of length 1 and you throw it on a grid like this of lines spaced by 1. And well, the needle can land on a line or not when you throw it, right? And the probability to intersect the grid is actually 2 over pi. And the proof, actually, that's an excellent exercise because there are many ways of modeling somehow these things. Either you take the middle, let's say, of the needle and then the angle, or many other things that you can use their coordinates somehow. And this gives different answers. So there's only one good answer. I mean, even if your computation is correct and everything, if you don't get over pi, you're completely wrong. So it's a modeling question. Then that's something important in mathematics. We're not here for doing abstract things, but also for understanding what you're doing, what we're modeling. So try to do this, and if you get over pi, have my congratulations. If not, even if your computation is correct, it's for nothing, it's garbage. So this means that you're not a good mathematician yet. Yeah, so try to do it. Very, very good question. Okay, now getting back to permutation, so we saw the probability for being a derangement is 1 over e. Now, what about, let's take the number of fixed points now. Okay, that's a random variable if you want, over Sn. And we know about this variable that the probability for it to be 0 is 1 over e. Well, here's the law in general. It's 1 over e at 0, and in general at k, if you want, the probability for having k fixed points, it's 1 over e, 1 over k factorial. So how to prove it? It's well, it's exactly as before inclusion exclusion, just modify a bit things and you get your probability here. So that's the law. And now the point is that this is the so-called Poisson law, so that's your definition. And more generally, so you see this is of mass 1 because that's the series of 1 over e. Now, well, you can define also Poisson of t if you want to throw in a parameter, like we did with the normal laws. You take the series of exponential of t, that's it, and you put t minus t here. So what we know so far is just that, well, this thing that the probability to have, for permutation to have no fixed point is 1 over e, and more generally that the law of fixed points follows Poisson of 1. Well, now that we introduce Poisson of t, I need to give you a result also about producing pt. And here it is. So you do exactly the same thing as before, but instead of taking the points from 1 to n, which are fixed, you truncate at the t, from 1 to the integer part of tn. And well, the number of fixed points between this and this, let's denote it by chi t, it's a random variable, follows pt. And so that's something that we know at T1. That's what we did. Now, in general, once again, yeah, inclusion, exclusion, modify bit things. And of course, when it goes to infinity, this integer part will disappear. I mean, all the formulas, you can just remove it like that. And because it's equivalent to Tn. So you'll just get some powers of T there. And try and get Poisson of T. So very good. So these are the Poisson laws. We have a lot of fun with them, with these fixed points. Now, well, let's do some theory too. I mean, we're proceeding here with Gaussian laws. Remember what we did was serious theory and then some fun with spheres and everything. I did a bit the opposite. So we did the fun first. Now let's do the serious stuff about Poisson. So first is that we have a one parameter family with respect to convolution. If you convolve two of them, you get this thing. In probability, this means that if two variables are independent, Poisson of S, Poisson of T, the sum is Poisson S plus T. But it's better, as I was telling you always, we're trying to have this point of view a bit abstract, so formulate things like this, okay? So why? Well, you convolve, the convolution of Dirac masses is just this. So you get a sum, and then here you use your binomial formula. That's it. Okay, very good. Now, another thing is that the Poisson laws actually appears as exponentials. So you see, that's exactly the formula of the exponential. But what I'm doing here is that the power, if you want, I replace it to the convolution. So it's exponential with respect to the convolution of measures. And this thing here actually is not a probability measure, it's a difference. So it's a bit tricky, okay? So that's the formula, is perfectly well defined, okay? And why is this true? Well, first of all, it's related to this. I mean, if you have a semigroup, it's power of something if you want, so that's your formula, okay? But let's prove it directly. So if you want to compute this, well, you get to decay here, and then once again, there's the fact that the convolution, where was it? Yeah, the convolution of Dirac masses is simply this. So this you can develop it with the binomial formula. You get something like this. And then, well, if you separate terms, here you get just the exponential of minus t. So you get Poisson of t. Very good. So we have results regarding the convolution. Now, let's prove the Poisson limit theorem. So here we need Fourier. So that's, here's the formula for your Fourier transform, which actually shows that that's another proof now for the facts that we have a one parameter semigroup because log f is linear in t. So you see this thing here that we proved in binomial things simply follows from this, if you know it. So how to prove it? I recall the Fourier transform is this. I mean, it's just a plain thing without any minuses or constants. So, well, it's just you take the formula of Poisson of t. When you're applying Fourier means the Dirac mass, which is here, delta k, to replace it by exponential ikx. So you get an exponential, and that's it. Exponential of exponential, if you want. Okay, so now ready to prove Poisson limit theorem, so that you take this Bernoulli here, and you convolve it 10 times with itself, and it goes to infinity, and it converges. This converges with PT. That's exactly as for the CLT. That's the reason why the Poisson limit theorem appears a bit everywhere. It comes from limiting theorems. So how to do this? We'll do it with Fourier. We'll compute the Fourier transform of this, and we'll get this guy here, the Fourier transform of PT. So on Dirac masses is like this, Fourier. So now I have two Dirac masses here. So by linearity, this is it. I raise to the power n now, because Fourier linearizes the convolution. And then I write it like this. And this is, remember that 1 plus 1 over n to the n goes to e, right? In general, 1 plus something over n to the n goes to exponential of that something. So you get this, but this was, let's go back, yeah, exactly the Fourier transform of PT. So you have proved the Poisson limiting theorem. Now, what else can we do? Well, we did limiting theorem, Fourier convolution. We also had all these finite groups, all that. We won't go back today. So the last thing which is missing now is the moments. And here, oh, this is yeah, this is very fun. So let's start with P1. There's no formula for the moments of P1. No formula. It's impossible. But what you can say is that these are the Bell numbers which count the partitions of 1K. Of course, you have recurrences, everything, a lot of formulas, but there's no explicit formula for these Bell numbers. So is this true? The moments of P1 are given by this. I mean, I just take the formula of P1, I replace delta S by S to the K, right? The case moment. And all the point is that, well, if you do some computations, you get this recurrence here, or these guys here. And that's exactly the recurrence for partitions, because if you want to count the partitions of 1K, how to do it? 1K plus K plus 1, okay? So I take 1K plus 1. I have to pair 1 with some guys here and to put it in the same partition. So I have to choose pair guys out of this K to put them in the same block with 1. And then the remaining K minus 1s, I have to make a partition out of them. So that's your recurrence. So finally, the moments of P1 are given by the same recurrence as the partition. So these are the Bell numbers. Very interesting. Now PT, now it's even more complicated. So, but it's a bit similar to what happened for the normal law. So normal law was counting pairing, and the parameter t was counting t to the number of blocks. Somehow each partition was contributing to this factor here. And well, that's your formula. And this is interesting. So now you have all partitions, and the blocks are non-trivial. So for the normal laws, it was just for fun. I mean, the blocks anyway, there are k over 2 of them. Now it's really partitions can have different blocks. So it's a non-trivial formula. So the idea is that, well, that's your formula for the moment, and you play with it a bit like before, but we haven't done this in the previous slides either, so we won't do it, and you're getting to these things here. These are the so-called Stirling numbers, I mean the coefficients of the various powers of t. So we'll get back to this a bit later. There's no need to prove these things because these are very related to cumulants. So when you do cumulants, you'll see these are actually very simple. That's more or less the definition of the cumulants. So I don't need to get into computations now. These are just some announcements if you want. These things which are good to know. So summary, now we have seen the normal Poisson laws. Well, apparently they are quite different, but that's what was the point of what we did today. So maybe for those of you who know probability, my weird way of explaining things was precisely in order to have the ground prepared for free probability. So we want to see what are the common features somehow of these things, which are a bit abstract. So first of all, limiting theorem, CLT, PLT. Then the moments are related to partitions, P2, the pairings and all the partitions. There are also some connection with groups and coordinates and things like that, with ON and the set. So next time, the integration of a compact group. So you see, this will explain this and this. So the item one, there's nothing you can do now except for doing applied probability with this, right? But when it's really belongs somehow to more pure mathematics, and these are very related. We are Brouwer type theorems, things like that. So we'll take a look at all this next time, and we'll do so-called Weingarten integration over groups, which will provide us with explanations for all these things, pairings, NSN. Okay, so see you next time.